My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 558. In this lecture, we will try to understand rectified linear unit, that is ReLU. So one of the big problems in the classical neural networks era, which is pre-2010, has been the vanishing gradient problem. It has been the vanishing gradient problem which is very often seen, especially when you are using sigmoid activation function or tan-h activation function. So when you have the problem of vanishing gradient, your convergence also slows down. Why? The reasoning is very simple, because if you have the vanishing gradient problem, the update is very small. What is my update? Your update is wkij new equal to wkij old minus eta into derivative of loss function with respect to weight. Now, if this derivative is very small, because of the chain rule, and just try to recall, because of the chain rule and because of multiplying numbers which are in between 0 and 1, and we are assuming here eta equal to 1, and if this number dou L by dou wkij is very small, then what is this number? This number dou L by dou wkij is very small. If this number is very small, then your old and new weights are very similar, which means you are not be able to converge to the solution fast enough, isn't it? And you will not be able to converge to the solution fast enough, and you will not be able to train very deep neural networks. You will be able to only train shallow networks, maybe 2-layer networks or 2 hidden layer networks, or maximum 3. But if you really want to train neural networks, you have to get rid of sigmoid and tan-h activations. Because of this problem of sigmoid and tan-h, around 2011, there is very elegant and probably one of the most important idea in deep learning called rectified linear units, in short form ReLUs, isn't it? Just this is I can say ReLU. So ReLU is one of the best activation function, and oftentimes it is used as a default activation function for lots of problems. Earlier, people used to use sigmoid or tan-h as default activation functions. That's the earlier people used to used this tan-h or sigmoid as default activation functions. But today, all of your activation functions by default is ReLU. Especially in multi-layer perceptrons. Yes, in multi-layer perceptrons, ReLU is by default activation function. Yes, if you are using a multi-layer perceptron, it's your default activation function is ReLU. There are other types of neural networks. We will see. We are now limiting our discussion to ReLUs to multi-layer perceptron. How does ReLU looks like? This is let me say this is my capital. This f is my activation function. What is f here? That is my activation function, and you have got a bunch of inputs. What are the inputs? x1, x2, so on, x1, x2, x3, x4, and we have weights associated with these inputs. What are the weights? w1, w2, w3, w4, isn't it? The input that I get here, what is my input here? The input here is w transpose x, where x is a vector. What is my x? X is a vector. Just see, the input for this f is w transpose x, and your x, this x is a vector, and even similar manner this w is also vector for this my f. what is my input? My input is W transpose X. Let me assume Z equal to W transpose X. Now this function f of Z, Z is input for f, therefore this function f of Z for ReLU is often written as f of Z equal to Z plus, isn't it? The definition of this is f of Z equal to Z plus, how can I say, maximum of 0 comma Z. And how does this work? F of Z, which is defined as max of 0 comma Z, what does it means? It means this function will be 0. This function will be, what is my function? This function will be 0 if Z less than or equal to 0 and it is equal to Z otherwise, isn't it? And how does function looks like if this value, I can say these are the on x-axis I have values of Z. How does f of Z looks like? F of Z looks like this for all the values which are negative. Let's assume this is origin. Which one is origin? Let me show. This is origin. Let me assume this is origin. When Z less than 0, just see, when Z less than, the value will be 0. What is Z less than 0? What is your f of Z value? If Z less than 0, f of Z is 0, isn't it? When Z greater than 0, Z greater than 0, here your Z is greater than 0, it is just the value of Z. Is Z greater than 0? What is f of Z value? F of Z equal Z. This is perfectly, I can say, how will it be? It is I can say a 45 degrees line, isn't it? This is how my f of Z looks like. Remember, we said any activation function should be differentiable, isn't it? If this f of Z, if this is my f of Z, what is my f of Z? F of Z equal to 0. If Z less than or equal to 0, f of Z equal to Z. Otherwise, if this is f of Z, how does derivative of f of Z with respect to Z look like? For this 45 degree line, what is the slope? The slope is exactly equal to 1, isn't it? What is my slope? How can I say? Just see, for this 45 degrees line, my slope tan theta, if theta equal to 45 means your tan theta means tan 45 is equal to 1. I can say this for this one is what, how can I interpret f of Z equal to Z? Otherwise means Z greater than 0. For Z greater than 0 region, which one is Z greater than 0 region? This is Z greater than 0 region. Therefore, what is my derivative? D by dz of f of Z when Z greater than 0. This is Z with respect to Z, differentiation is 1. That is tan 45. That is tan 45 degrees. What is my tan 45 degrees? Which is equal to 1, because tan 45 is equal to 1. Derivative is 1. The slope is always equal to 1 if while Z greater, if your value is if Z is greater than 0, your slope is always equal to 1, isn't it? It is always constant. Here, if you observe in this direction, what happens? Just see this one. Here your theta equal to 0, therefore your tan theta, slope means tan 0 equal to 0. It is always constant. Slope is equal to 0. Constant means derivative is 0. There is one problem here, because function is not continuous at origin, isn't it? Just see, this function f of Z is not continuous at origin. Why? Because it is not smooth one, isn't it? Function is not continuous at origin. ReLU activation function is not differentiable at Z equal to 0, isn't it? What is my ReLU activation function? It is not differentiable at Z equal to 0. Derivative everywhere is defined except at origin. At origin, the derivative is not defined because it is not a smooth curve, isn't it? The derivative of this activation function is equal to 1 or equal to 0. This is very interesting idea. We will see the advantages and disadvantages of this in my next lecture. I request all of you to go through this lecture. I will continue my discussion on ReLU activation function in my next lecture also, that is lecture number 559. Thank you very much.